Hello, everyone. So I'm going to talk about the SDK, the software development kit that we have for P4 and C programming. First of all, we're going to go over the SDK and the overview of SDK. What is the SDK? And then we dive into the toolchain a little bit and see how the steps and the details of the toolchain for the C compiler and P4 compiler would be. And then we cover debugging methodology that we use and the platforms that we are supporting for the SmartNIC. So the SDK is basically a integrated development environment or the IDE that runs natively on Windows. It's developed on Windows using Visual Studio and C++, and it natively runs on Windows. It also can run on VMs, Windows VMs, and also under Wine on Linux or Mac. It gives you the ability, the complete package for doing development on a SmartNIC, from editing your code, building your code, debugging it, optimizing it, and so on. It supports all the data plane programming, and it comes with libraries and all other blocks that actually helps you to program the data plane. It supports a couple platforms. We support the cycle accurate simulator of the SmartNIC. So you can use the simulator to simulate the SmartNIC and run your application. Or you can talk directly to the hardware, which runs the network flow processor. And also, it comes with a full documentation in HTML and PDF format as a standard. So SDK components, the front end that what you see is the IDE called Program Studio. It includes the tools for building your program, such as assembler, C compiler, P4 compiler, linker and loader. And also, it supports the C scripting through the cling command line. So you can run a C script even while your application is running. And it talks to simulators. It's not supported on the hardware yet, but the C scripting is only supported on the simulator at the moment. Of course, it comes with the hardware debug servers that basically talks to the hardware, and also the simulator, which comes with the SDK. Yes, it is a cycle accurate simulator. So here's how the Program Studio looks like. When you open it, you will see only the firmware and also the documentation that comes with the SDK in the work projects, the project space area. Oops. On this area here. It gives you the ability to manage your projects because it's a project-based IDE. So you can take a snapshot of your project in the different stage of your development, and you can refer back to it if you need to. So it helps the organizing and developing ongoing projects. Also, the project types that you can create and maintain with the SDK, it's two different ways that you can create the project. There's a standard project, which is the C project. This standard project can be a debug-only project, which means you build the object file outside the Program Studio, for example, using the command line on Linux or on Mac. And you have the object file, and you want to use the IDE to load and debug it. So you can use a debug-only project which doesn't contain any source code. And also, of course, you can use P4 project to program your SmartNIC using P4 language. It's based on the document interface or MDI interface design. So it's the same mainframe used for different mode in the SDK. The mode would be debugging mode or editing and building mode. So you don't need to leave the same mainframe to run the debugger or leave the mainframe to edit or build your debugger. So you're using the same mainframe. The mainframe itself updates itself based on what mode you're in. A little bit talk about the project space, which is the most important area in the SDK, where you basically have access to your files, to your debugging threads or cores, and where the documentation is. It's a dockable window on the right-hand side, or you can move it, but by default, it would be on the right-hand side of the Program Studio. When you're opening the Program Studio for the first time, you will only see the file view, which gives you a pointer or a link to your documentations that comes with SDK. When you're creating your project and you're putting the file to your project, you will have the file view, which gives you the files within the view and also the dependencies of your file. For example, if your file included a header file or included a P4 file or a C file, it comes as a dependency. And you can search through your project, the macros that has been used within your project or the function that has been used from your project. You can search them and look at them either by name or by files. It's an easy way to get to your files and all the dependent files that exist in your project. And as you go on and build your project and load it to your simulator or to your hardware, you will be getting the thread view, which is on this side, that gives you the view of the threads or every little single cores that are in the chip. As Johan mentioned, it can go up to 960 threads, 120 macro engine, each 8 threads, so it can get complicated if you don't have the visibility to all those threads. C compiler that comes with the Program Studio, it's accept the standard C notations. And so such as like a pragma and specifiers, such as declaring a space for explicitly specifying the memory in your application and the type of that memory that you're using. Different type of memory is available on the NFP, either on board or on chip or on board. And also it gives you the different properties of the variables or the memories that you're using. Either it's a local or it's a global. It accepts the inline assembly through the ASM statements. You will see some of them probably in our labs later on. The optimization on the C program is based on the whole program mode, which means your functions or macros that you are using in your program is not based on the single file that is function or macro has been used. Is based on the whole program that has been compiling. So it's based on the context of which that actually that functions or that macro is going to be used. And it generates the object code that with the extension of .list. And this .list files later on will be fed into the linker to create the binary. The P4 compiler, it's basically come with Program Studio contains the two parts, front end and the back end. The front end takes your P4 file, which has a .p4 extension, and it creates the intermediate representation of the P4 or IR. It's based on YAML format, and that later on will be fed to the backend, and the backend will takes optionally the data plane libraries that comes with the Program Studio to generate the NFFW file or the ELF-based file to be loaded to the SmartNIC. So the backend basically is what the P4 would, the P4 file would be at the end when it's gonna go to the SmartNIC. So it's an architect-dependent portion of the P4 compiler. The block in here, the data plane libraries and the standard libraries that comes standard with Program Studio, it's basically facilitated and enabled development and easily accessing the different part of the network, the NFP chip. The features like packet I/O and buffer allocation and freeing, ring allocation and freeing, and so on. Basically, it comes and supplied with the Program Studio and optionally can be pulled into your P4 application. The standard libraries that comes with it, it basically facilitates the functionality like packet reordering or flow cache and so on. So the linker and loader, it goes hand to hand in SDK. If you recall, the output of the P4 compiler or the C compiler would be the .list file, which is the object code, which is going to be input to the linker. Linker will basically combines these different list files that has been generated from your application and combine them together. It resolves any symbols and allocates memory for the object file, which is the NFFW file. So basically, the steps that the loader and linker takes, the loader takes is reading that NFFW file, which is the output of the linker, and verify that it's actually for the valid target. Then it's perform the reallocation and resolving symbols within your applications. The loader supports the import variables, so you can import your own variable on top of your NFFW file, and the loader will basically resolve any conflict that those import variables might have with your object file. And then it attempts to stop or interrupt the hardware. If the hardware or the simulator is running and you attempt to load a new firmware, it gracefully tries to stop it. If it cannot, it resets it. And then start loading. It verifies and set up and configure the CSRs for the chip, and then starts loading the memory section. That excludes the code section. So the memory that is being used in the code is a generic memory sections that is on the NFP. And it loads the initialization code section and then execute the initialization section if there is any initialization that needed in your application. Some application needs to initialize the MAC, SerDes, and so on. So that part is being done in the initialization section. And at the end, it will load the code section. And it basically triggers the event in the IDE that tells, okay, the application is loaded and is ready to run.
Question.
Yes.
How long would it typically take the whole application? How long would be the downtime when you loaded the complete new version of the firmware?
Well, it depends on the application. For example, for the P4 application that we are using in the demo, there's a lot of initialization going on. And that would take probably about 30 to 45 seconds load time and initialization, the memories and initialization, the NBI and MAC.
Reboot the code before you are able to actually pass traffic and complete end-to-end time would be like
After you load and the initialization is done, you're able to pass traffic. As soon as you run the target, you will be able to run traffic through. Yes? Are there any situations that you can't
provide certain checkpoints. Like, for example, scenarios like fire alarms.
Right.
Like full sorters when they do like really want to switch things directly in the ship while the traffic is flowing.
Well, not at the moment. This is something that is in the horizon that is coming, but not at the moment. The notion of loading separate micro engines while the other micro engines are running, that is not supported yet, but it's something that is coming. The debugging platform that the SDK supports, it supports, as I said, simulator and the hardware. Simulator can run locally on a host that is the program studio or the SDK is running. So both of them will be running on the Windows. Either that is a VM or using Wine. Or you can access simulator remotely. So the simulator running on the Linux or a Windows on somewhere on the network, and you can remotely access to the simulator and stop it, debug it, and so on. Also, as you will see, the hardware debugging, again, the Program Studio SDKs run on the Windows platform, and the debug server or debug agents run on the Linux where the SmartNIC is installed on the server. This is give you basically a comparison between features that are available on the simulator and the hardware. There are more features available on simulator than hardware simply because we cannot interrupt the hardware to do a lot of features that we are supporting on simulator. In simulator, of course, is a little bit slower than running on the hardware. So that's the low key for the simulator. But in general, it saves you time in debugging and tuning your application performance-wise, memory size-wise, and so on. So at the end, it pays the time that you're spending on simulator than running on the hardware for the first time, because debugging on hardware is not easy. Although we provide a lot of features that this facilitates debugging on the hardware, but always debugging and tuning application on simulator is easier than hardware. Features that are really exciting on simulator is code execution coverage. So basically, it tells you there's a feature that you can call and enable in simulator that gives you the code coverage. For example, you have a 10 instruction in your application, and it tells you, okay, this instruction number 1, it executes 8 times, instruction number 3 executes 10 times, but the instruction number 2 never executed. So you can go back and say, hey, why my instruction is not being executed, or do I need this instruction at all? So it gives you the debugging features such as this to go and optimize your application. Also, it comes with the command execution history of your application. So you're running your application. The application issues a lot of commands that goes through the bus and reaches the target, and then, for example, query for reading the memory or writing the memory, or I/O query. These are commands that is traveling on the bus. You can go back and in time and find out, okay, I issued this command, that the signals never come back, and I'm stuck. Why this happens, when this happens. So this history collection helps you to go back in time and find any bug that your application might have. And as I said, hardware is faster than simulators. Yes. It's both. You can see the execution coverage for both. Basically, if you're programming in C, your source view is in C. Of course, at the back end, you have the instruction which maps to the controller store of each micro engines. But in the front, you will see your source line of your C. And if, for example, your source line is a function call, then there would be more than one instruction per that source line. Then you can basically step through that functions and find out what, how many instructions that function would be. And it gives you the coverage in general for the specific function. So for example, you have a memory read function that you implement for yourself, and that takes maybe 6 instructions or 6 lines of code to read the memory, verify it, or whatever you want to do with the memory. So it gives you, on the source line, it tells you, okay, this functions or this source line has been called 120 times. But when you step inside that functions, you will see that 120 times. If your function has a 6 line, maybe 20 times each line. So it gives you the total of the execution for that specific function. Yes, you can. Well, in general, you really don't need to use the assembly in the C code unless there is some critical section of your application that needs a very high throughput and high performance. There are documentation comes with it that it facilitates the learning curve for the instruction, the architecture instructions, and how you can use the assembly. But the standard libraries comes with the SDK, and the C standard libraries come with the SDK. Is pretty much you pretty much don't need the assembly because it tells you, for example, for these intrinsic functions or these functions that comes with the standard libraries, you need 20 cycles for this instruction. For these function calls, and this is how many source line this function call is. So those are standard libraries, which basically it covers the use or need to use of the assembly. As I said, the simulator is a cycle accurate, and for all the data plane functionality on the chip. It covers the full chip, which all the memories on the chip, all the microengines, and so on. It basically gives you the easy way of profiling and debugging your application using the user interface, a friendly user interface, which is the Program Studio as an IDE. And also gives you the rapid prototype of your application, even your hardware development is going on, and you wanted to start your application. You can use the simulator, and the parallel between the software and hardware development can be achieved. I mentioned the history collections. I want to dive a little bit into this because it's a really powerful features of the simulator. It tracks basically the idea here is you track the reference that your application makes and the commands that the application issues while it's running. So the thread is collected in 3 different ways. It's the events that your application generates that run through the event bus, the command that has been generated in your applications that goes through the I/O bus or the memory bus. It's called command push pull bus in our chip, and also the commands that goes on the DSF CPP or the distributed switch fabric. So each microengine internally has the CPP bus to it, and for the microengines that are talking to each other in different block in the chip or different island in the chip, it's a DSF CPP or a mesh that goes around the chip for the connectivity between different blocks. So it covers all those buses in your chip. And so you can go back and find out what command has been issued, and if the signals or the micro engines that is issued that command is not executing anymore, what was the reason? It was the command that has been issued and the signal never come back, or I'm waiting on the wrong signals. This is, by the way, is a very common bug that is in the applications. The application issues a command and waiting on a wrong signal. For example, the memory blocks signal back with the signal, let's say, number 4, but the application is waiting on signal number 5. And it never gets the signal back, and you wonder why this is happening. So this will help you to catch those bugs. Yes? This is only for the chip itself.
I know, but it's very similar to the same amount of risk. Can give me also the, because you mentioned, can also tell me the polling the execution path.
Yes.
And this can give me about different parallel paths that are running inside the chip.
Yes.
What is actually affecting the.
Exactly. Yes.
How about the crashes? I mean, does the ship crash at some time? One time does have a concept of core bump or anything like this?
You can save the so on the simulator, when you're running and in basically simulator crashes, the IDE itself is not crashed. It's the simulator or the hardware is crashed. So you still have the visibility to this on the hardware, because this data is collected on the host, is not on the server, is not on the simulator, is on the host and is within the IDE. So you can basically go back and see what happened. I'm sorry, I didn't. This is not specifically for the performance. This is for debugging. For debugging. For the performance, we do have the performance analyzer only for a specific micro engines. So you can call this performance analyzer for the specific micro engine and find out what percentage of the time this micro engine was executed, what percentage of the time this micro engine was idle or stalled, how many percentage of the bus this micro engines occupy, and so on.
I would argue this time strip chart is actually much more useful that you can see, who's actually executing, who's blocking, and what they're waiting for, which is usually the root cause of performance problems.
That's what it is, yes, basically.
Who's active, who's idle.
Exactly.
Idle. So the time chart's actually much more useful than like a percentage group.
Well, that's for the, we had users that wanted to collect the data and save it in the spreadsheets. And that gives you the ability to save this performance analyze in the spreadsheets, and for later on if you want to refer to it. Okay, that's basically it. If I have 5 minutes, I'm running some application. This is the same application Johan mentioned, and show you the simple RX and takes application that has been written in C. I'm running it on the simulator, and here's the codes look like in the simulator with your instructions, addresses. So I wanted to just stop this and show you these history collections that I was talking about, so you will get a sense of what actually I'm talking about. Yes?
You can use a bigger and bolder typeface, especially for that.
Yes, I can actually change the font in the Program Studio, so if that helps. Is it better?
That's a little better, but bold would be better. Bold face.
Okay. No, I still want to text. Don't go there.
Choose the font, make it bold rather than.
You don't, I can't recall. No, you cannot make it bold.
Another typeface would be bolder instead of like this too much time. So the courier new is bold, and the others are bold. That's the one better.
Okay. Is it better? There you go. Okay, so this is, as I mentioned, this is the same screenshot that Johan had in his slides. It's it basically it's just takes the traffic which comes through the PCIe or the network, and it depends on that. It depends on that. It will receive it and then transmit it. It will check if there is any error. It's in the receive the data, and if it is, then it's basically do the counters. So that's how you basically you can keep counters. You have a CSR called mailbox, and you can increase it and use it as a counter. So, but this is the history collection I was talking about. So if I go to the beginning of this application, you see this command that has been issued by this microengines, and that's the external memory swap of 2 quad words, which is 4 long words, and it tells you that what address that memory has been read or swapped, and what signals is being used for memory unit to signal back the microengines after the swap is done. And also it tells you which microengines, in this case is the microengines island 4, microengine 0, and which thread within this microengine issued this command, and it issues this command for itself, for its thread, or some other threads within the microengines, or some other threads with the different microengines. And what signal is used for that event. And also it gives you the type of this command, which is the reference in this case, and which program counters this issue has been issued, and what cycle this command has been issued. So if I go back to slides, I can explain this a little bit more detail. In here, so you will see this line here that it basically says the reference is started. It's the when microengines actually request the arbitration to get arbitration of the bus. So that's when the command has been issued or the execution happens in your code. And this is when this part here is when actually the microengines get the bus and enqueues this to its command FIFO. All these, so the microengines can issue multiple commands in a different instructions, and it doesn't have to wait because it has to use the queue to actually queue this command, and depends on the block or depends on the component within the chip. There is a different depth to this queue. So this is microengine is enqueued the command. This is when the microengine's removed, when the command has been removed from the queue. This is from when the command is processing done and it went to the, in this case, external memory. And then it's been processed and its processing is done, which is going to be right here. And then the triangle, it says, okay, the processing is done within the block, and the microengines is signaled back. And this is when the microengines consume the signals and keep continuing. So I guess I'm running out of time, and I'm actually over my time. So if there is any questions, I will be more than happy to answer it. Otherwise, please, we're on break now. We're taking break now.